Hey guys, welcome to part 2 of solving IIT JAM 2026 problems. I once again got three problems here with me today, and I'll be attempting to get the solution to each of these. So here we go. So I've been given a potential, and if you notice, you can write the denominator as r square. So, okay. So first option asks me whether the force is central, and the answer is no, because as you all know, central forces exclusively depend on r and are pointed in the r cap direction. And for a non-central potential, the force cannot be central. So thus, option A is incorrect. Now, checking option B. Okay, so option B is correct. Why? Because uh, non-central forces have non-zero torque, and torque is defined this way. So if your force is not central, torque need not be zero, and thus your angular momentum, the time change of angular momentum, is also not zero because the time derivative of angular momentum is tau. So option B is in fact correct. Now checking option C, they're asking me whether linear momentum is conserved or not in the y direction. So we gotta check if dpy by dt is zero or non-zero. Okay, in order to do that, I'll use this definition that force is the negative gradient of potential. So the y component of your force would be minus dou v by dou y, and that y component of force is also equal to dpy by dt, right? I'll add another page here. So is dou v by dou y, what is it? Okay, so clearly from the expression that we obtained here, we observe that this is not zero. Yeah, you can take the quotient rule and find out the derivative, and you'll see that it's not zero. So you can straight away tell that this is also not zero, and thus linear momentum along y direction is not conserved. Option C is incorrect. Option D, moving on to option D, they're asking me whether energy is conserved or not. Oh, V is independent of time, right? If V is independent of time, Hamiltonian, which is given by kinetic energy plus potential energy, is also independent of time. So there's no reason to believe that E is not conserved. So E is no reason to believe. So option D is incorrect. E is definitely conserved, right? So now we're done with problem one. Now we'll move to problem number two, right? So I've been given that my fields are E and B in rest frame, and then they are E prime and B prime in a moving frame. This moving frame is moving with a velocity vector v naught, and they've given me that through Gaussian transformation, my Lorentz force is invariant. So if the Lorentz force is F here and it's F prime here, they both are equal. Right? It's already given in the question in case you didn't know that. Now they're asking me the relationship between uh, the electric field and the magnetic field in the rest frame and in the moving frame. Okay, so it's very simple. Yeah, so let me just draw two frames here. Let this be the moving frame, and let's say it's moving with uh, let me draw a vector diagram to better illustrate this, right? And let's say there's a particle in the rest frame which has a velocity vector in this direction, and let's say this frame is moving along this direction, and this vector, which I'll call v prime, is a velocity vector of that particle, some particle in as observed in the moving frame. So the vector relationship is vector v equals uh, okay, vector v minus no, hold on. Yeah, it's vector v minus vector v naught is vector v prime. Okay, all good. And now I can write vector v as vector v prime plus vector v naught. Okay, now let me just add the expression for f in the rest frame. It's q times e plus v cross v. Q is again invariant because it's charged. There's a conservation of charge applied, universal conservation of charge. So I will plug this vector expression here to get this. Okay, I'll hold on to this equation for now. And then now let me write the Lorentz force vector in the moving frame. Okay, yeah, that's good. Okay, let me. Okay, so if you compare these two equations, you notice that E prime can be written as E plus V naught cross B, and B prime is just B. So, which option does this correspond to? So, yeah, this corresponds to option number B. Cool. Yeah, now let's move on to the last problem. It's an operational amplifier problem. They're asking me to find V naught. They've given me the two inverting and non-inverting inputs, the voltage. Mm. Okay, so this is a this looks to be a subtractor circuit, and if you knew the result already, you could go ahead and just move on with the next problem because it's option A. But here we'll be uh, learning how to get the answer. So right. So if you notice this branch, I will use voltage divider rule to find out. Okay, this is V plus. This node here, the voltage there is V plus, and at this node the voltage is V minus. I'll be using the voltage divider rule to find what V plus is, and it's very simple. It's V1 times the second resistor uh, with a sum of two resistors, so 2R. So V1, V plus is at the potential V1 over 2. Now, because of negative feedback and virtual short, V minus is also at this potential. Cool. Now that I have that, I'll go ahead and use KCL, the current equation. Let me call this IF, and I'll just call this I don't know, I, for example. So using KCL, and yeah, because of ideal op-amp characteristics, no current enters the op-amp, so every current goes like this, right? So from KCL, I say that II equals IF, and you use Ohm's law. So V2 minus V minus over phi R, that should be equal to V minus minus V naught by phi R. And those supplies, the denominators cancel. And V2, so if that goes there, I have minus 2 V minus, which is equals to minus V naught, or uh, wait, let me just make space for this. Yeah. So V naught equals 2V minus minus V2, and V minus we previously determined it's V1 over 2, so it's just V1 minus V2. So there we have it. We found out the expression for the output voltage, which matches option A. Yeah, so that is it, guys. Thanks for watching this video. I'll be coming up with part 3 soon. Stay tuned. Bye bye.